Section 5.6. Hess's Law. Many enthalpies of reaction have been measured and tabulated. In this section and in the next, we'll see that it's often possible to calculate the delta H for a reaction from the tabulated delta H values of other reactions. Thus, it's not necessary to take calorimetric measurements for all reactions. Because enthalpy is a state function, the enthalpy change, delta H, associated with any chemical process depends only on the amount of matter that undergoes a change on the nature of the initial state of the reactants and the final state of the products. This means that whether a particular reaction is carried out in one step or in a series of steps, the sum of the enthalpy changes associated with the individual steps must be the same as the enthalpy change associated with the one-step process. As an example, the combustion of methane gas, CH4, form carbon dioxide gas and liquid water can be thought of as occurring in two steps. One, the combustion of methane to form carbon dioxide gas and gaseous water, and two, the condensation of gaseous water to form liquid water. The enthalpy change for the overall process is simply the sum of the enthalpy changes for these two steps. The net equation is methane plus oxygen yields carbon dioxide and liquid water with an enthalpy change of negative 890 kilojoules. To obtain the net equation, the sum of the reactants of the two equations is placed on one side of the arrow and the sum of the products on the other side. Because two waters occur on both sides, it can be canceled out like an algebraic quantity that appears on both sides of an equal sign. Figure 520 compares the two-step reaction with the direct one. Figure 520, an enthalpy diagram comparing a one-step and two-step process for a reaction. The enthalpy change of the direct reaction on the left equals the sum of the two steps on the right. That is, the delta H for the overall reaction equals the sum of the delta H values for the two steps shown. Hess's law states that if a reaction is carried out in a series of steps, delta H for the overall reaction will equal the sum of the enthalpy changes for the individual steps. The overall enthalpy change for the process is independent of the number of steps or the particular nature of the path by which the reaction is carried out. This principle is consequent to the fact that enthalpy is a state function, and delta H is therefore independent of the path between the initial and final states. We can therefore calculate delta H for any process as long as we find a route for which delta H is known for each step. This means that a relatively small number of experimental measurements can be used to calculate delta H for a vast number of different reactions. Hess's law provides a useful means of calculating energy changes that are difficult to measure directly. For instance, it's possible to measure directly the enthalpy for the combination of carbon to form carbon monoxide. Combustion of 1 mole of carbon with half a mole of oxygen produces carbon monoxide and carbon dioxide, leaving some carbon unreacted. However, solid carbon and carbon monoxide can both be completely burned in oxygen to produce carbon dioxide. We can then use the enthalpy changes of these reactions to calculate the heat of combustion of carbon to carbon monoxide, as shown in figure 5.8. The key point of these examples is that enthalpy is a state function. So for a particular set of reactants and products, the change in enthalpy is the same whether the reaction takes place in one step or in a series of steps. For example, consider the reaction of methane and oxygen to form carbon dioxide and water. We can envision the reaction forming carbon dioxide directly or with the initial formation of carbon monoxide, which is then combusted to carbon dioxide. These two paths are compared in figure 521. Because enthalpy is a state function, both paths must produce the same value of delta H. In the enthalpy diagram, that means that the enthalpy of enthalpy 1 equals the sum of enthalpy 2 and 3. Figure 521. The enthalpy diagram illustrating Hess's law. Because enthalpy is a state function, the enthalpy change for the combustion of 1 mole of methane is independent of whether the reaction takes place in one step more than one step. So on the left you have a one-step process where methane and oxygen burn, or methane burns in oxygen to form carbon dioxide and water. The overall reaction is 890 kilojoules of energy released, so it's an exothermic reaction. If you were to instead say, well, methane probably creates carbon monoxide and water and some oxygen, and then the carbon monoxide goes into carbon dioxide, both of these reactions equal the overall reaction. So it doesn't matter how many steps that it is, the overall reaction is the same amount of energy. So instead of doing an experiment for every possible reaction, you can do a few reactions like this and then just add them up to find out what the energy change is for the reaction that you're looking at.